Hello everyone and welcome into the first episode of From MAKiTs workshop, and today we'll be making sulfuric acid. Now you might be wondering how this relates to sulfuric acid, and the answer is it doesn't. It's just that sulfuric acid got so normalized these days that in order to actually hook people into watching video about acidity, bases, chemistry, doing reactions in chemistry, doing reactions safely in chemistry, I have to resort to this. I blame the internet. Yeah, so we'll make a bucket of sulfuric acid. But how do we make this sulfuric acid? Well, I'm so glad you asked. You see, I've got a lot of sulfur. This isn't even all the sulfur I have. I have crazy lot. I don't know why I bought it. It was cheap, so I thought, wow, it's a bargain, but it's a serious problem. So I thought maybe we could take this sulfur, right? Burn it to make sulfur dioxide, then oxidize to create sulfur trioxide, then take the sulfur trioxide, dissolve in water, and boom, sulfuric acid, magic. Now yes, there are certain complications that come with this process, like for example, I know, there's a lot of heat when you dissolve sulfur trioxide in water, a lot of heat is happening, so that's kind of a problem, but you know, these are all minor hiccups. And yeah, due to how many videos I've made recently with Harry from Scrap Science, I did ask Harry, and yeah, Harry did strongly advise against it, but what does he know, okay? Harry is just an actual expert chemist from whom I got almost all of my practical chemical knowledge, has been doing chemistry publicly for over 6 years, whose second video on the channel was about making sulfuric acid, and actually half a year ago attempted making sulfuric acid using this precise reaction. You know, now that I say that loud, maybe we should actually... Okay, so let's revise for a second. We take sulfur, we burn it, sulfur dioxide, sulfur trioxide. Actually, what are the dangers of sulfur trioxide? That's a good question. Well, when it comes to ice, it burns them. When it comes to skin, it burns it. When it comes to the gastrointestinal tract, it burns it and may be fatal when inhaled. Now, I like breathing. I wouldn't say I'm an addict, but I tend to do it quite often, and so not breathing for the entire process, that's gonna be kind of a pass on my side, you know. So how about plan B? Copper sulfate. These two are unrelated, therefore a different video. If you'd like to learn more about that, go to Patreon. So, this is copper sulfate. And the basic idea will look like this. We'll take this copper sulfate, dissolve it in water, electrolysis, magic, sulfuric acid. You don't want to do it for too long either. No, one cable was dark. It didn't really work. It's still blue. It really shouldn't be blue. There was like a weird thing forming on the cable too. What did I do wrong? I mean, I dropped in some copper sulfate into water, and then I submerged two cables with electricity in them, and it should have worked, right? I mean, we did electrolysis. So what's wrong? This doesn't make any sense.
Hi, maybe I could help with that.
Hi, that's Harry from channel Scrap Science. You might have seen him already on the channel. We actually finished the video on Harry's channel about... what was the video about? It was about It was about...
Electrolysis, yeah.
Yes, electrolysis, that's true. Wait. Electrolysis? And right now I'm trying to do electrolysis. Harry, you're an electrochemist. Do you have any idea why this wouldn't be working?
Basically, your acid generation reaction relies on two half reactions, one occurring on each electrode. A reduction happens on the cathode and an oxidation happens on the anode. Now, on your cathode, the easiest reduction half reaction to do is the reduction of copper ions into copper metal. You're using copper sulfate specifically because copper ions are so easy to reduce and effectively remove from solution. There are no issues here. The problem, however, is your anode. The half reaction that you want to happen here is the oxidation of water to make oxygen gas and hydrogen ions. What you'd effectively be doing overall is removing the copper ions from solution on the cathode and adding hydrogen ions in on the anode, making sulfuric acid. This oxidation is actually a really difficult one to perform though. If it has the option, your anode will do an easier oxidation reaction, and the oxidation of the electrode material is a prime candidate. In the case of using a copper anode, the oxidation of copper is much easier than the oxidation of water. By using a copper anode, you're oxidizing copper on one side and then you're just reducing it on the other. In solution, you're not really generating anything overall, let alone any acid. And you've pretty much just set up a copper plating experiment.
Ah, I see! So that's what's happening. I'm still in the same spot. I haven't actually edited that segment yet, so I'm going to just assume that this is actually the copper plating experiment and this is not actually doing electrolysis because we're just moving copper ions from one electrode to the other. It's just a wild guess. But yeah, this is the surface level idea of why this is a copper plating experiment and not electrolysis. If you actually like to learn more about electrolysis, how to do electrolysis, what is electrolysis all about, then watch video on Harry's channel, because I'm not going to cover that here. Instead, we'll just go straight for it. And for that, we basically need a different electrode. Damn, I always forget which one is the cathode, which one is anode. You know what, this is gone for too long already, and I got some water, so let's put it out. Oh, no. Alright, so let's start the protagonist, copper sulfate. This is what it looks like, and the name can already tell us a lot about it, because you see, this is copper, and this is sulfate. Copper here is positively charged, sulfate is negatively charged. So, oversimplifying it a bit, you can think about it like this. These oxygens have too many electrons. This copper has too few electrons. And if you've seen my video about bonding, then you know that this will cause them to bond ionically. Now, when we dissolve it in water, it forms copper sulfate pentahydrate, and what's really nice is that we can calculate exactly how much copper sulfate we need to dissolve. In order to calculate that, we just note down the mass of a single molecule of copper sulfate, which is equal to around 265 yoctograms. Then we note down the mass of a single molecule of water, which is around 29.9 yoctograms. And we remember that for each copper sulfate molecule, we want 5 molecules of water, because pentahydrate, penta means 5. So we take these, and there, for each 265 yoctograms of copper sulfate, we want 149.5 yoctograms of water. Or, in order to make it a bit easier for us, we can multiply both sides by 10 to the 24th power, here represented by capital N, in order to realize that for each 265 grams of copper sulfate we need around 149.5 grams of water. Now, what's really nice is that this sulfate will remain in the solution no matter what, so if we turn all of this copper sulfate to sulfuric acid, then what that means is that we'll get the exact same amount of molecules, but this time of sulfuric acid. And if we repeat the process of getting the molecule mass, multiplying it by the number of molecules, then we get this, which means that out of each 265 grams of copper sulfate we add in, we should get back around 163 grams of sulfuric acid. And that's cool and all, but that's not all we can calculate. You see, as it just so happens, in order for this reaction to happen, we need 1 electron for each hydrogen. There is a bit more depth to it, but that's the basic idea, which is really nice because based on this, we can actually predict how many electrons we need. So that's great, except how is that supposed to help us? I mean, yeah, this does tell us how many coulombs of negative charge we need, but that's not really useful. If only there was some sort of unit that would tell us the amount of negative charge per second. You know, if only there was some sort of unit, something like coulombs per second. Oh, would you look at that! Amperes! So yeah, because we know that we need 2 electrons per sulfuric acid molecule, we can actually get the amount of coulombs we need, and because of that we can get the amount of time based on the amperage, which is extremely useful. If not for the fact that yours truly bought a voltage supply instead of a current supply, because I kind of ran out of funds for the video, but that doesn't matter. The point is, we could figure out hypothetically. And also we can figure out based on the color. Anyhow, here's some fun footage. Now that it's on 0, we can go like this. And now, let it rip. Maybe not all the way up, maybe like... I hear this. It's doing something! I did it backwards. Wait, did I do it backwards? I can't tell. There's so much copper on this. There's so much copper on this side. Wait. I think it's walking. Yeah, I think it's walking. Okay, I just finished a stream with Tefta, and what perfect timing I have. I think I bumped the wire, I think that's why it happened, but it started smoking a lot. That's banned. Now what we're gonna do is we're gonna dismantle this. Now we have to do it. It's 2 AM, I'm really tired, but it doesn't matter. That's been electroded. So many cold. And so there we go, it is finished. Now I say it, not sulfuric acid, because I don't think this is sulfuric acid. First of all, it's really blue, which is, well, kind of a giveaway. But second of all, I tried mixing it with some potassium hydroxide, and also I tried pouring it over a leaf, and it like didn't corrode anything. And we all know that acids eat away organic things, so it should have absolutely demolished this leaf. So yeah, it's probably not an acid, because that's what acids do, right? They react with bases and they eat away organic things. Except, what if they don't? Wait, what are acids? Okay, so I know it didn't work last time, but this time I've got a whole liter, so... Oh, it's fine, we can put it out, you can just... There. Oh, why did I do it again? Oh, that was such a bad idea. So, why didn't it burn the leaf? And what are acids, actually? Well, contrary to popular belief, acids aren't really dangerous. I mean, they are, yeah, most of them actually are dangerous, so, you know, do be careful, but that's not really their defining characteristic. Basically, you have acids and bases, and the way they actually work is acids would really gladly accept negative charge, and bases would really gladly donate negative charge, and that's kind of it. Now, what does that mean? Well, for them we have mostly 2 definitions, Lewis and Lowry, and here's how they work. For Lewis, the acid borrows electrons from the base. For the Lowry, the base borrows proton from the acid, and in both cases this amounts to the same idea, the same movement of charge, but the method is different. And honestly, when it comes to acids, we'll have to wait for the organic chemistry video, because that topic is deep, but that's the basic idea, and that's how you should think of acids, not as these dangerous chemicals that eat away everything that's alive, only kind of like ions or salts. Because of the whole charge thing, they're actually extremely similar, so that's to say that depends on which one you're talking about. Anyhow, here's some more footage. Yep, the black thing seems to be staying roughly on this. This is just like an initial filtering stuff. Yep, it's not going through. Okay, phenomenal. I'm a chemist, Harry. You're a chemist, Harry. You're a chemist, MAKiT. I'm a chemist, Hagrid. Okay. No, I'm gonna need my laptop for this one. Yes, a bit dangerous, I know, but oh well, I already did it. The point is, into our thingamajig, and then, secondly, tape. I mean, tape. So now it's time for the last segment, which is safety. Because you see, yeah, in this video it might seem extremely irresponsible of me to play with fire like this, throw acid around, and yeah, it certainly does seem irresponsible, but that's only because it's supposed to seem irresponsible. And in reality, it's all under control. And here's where we come to safety, but not the kind of safety you're thinking of. You know, really often, when people get into chemistry, they're warned with safety. And they learn the rules like, oh, don't drink anything from a lab, don't sniff anything from a lab, don't touch anything from a lab, just don't be in the lab in the general. And those rules, yes, they do tend to save some lives, but they are the wrong kinds of rules. Because, you see, the dangers we know about aren't really that dangerous. And I'm not gonna just stand here and tell you to not do dangerous things. Go ahead, do the dangerous things. That's actually a pretty big part of science. However, when it comes to the dangers that we're aware of, they're not really a problem. The real problem are the dangers we're not aware of. So, for example, when it comes to sulfuric acid, I could have just attempted making sulfuric acid using the sulfur trioxide method, right? I could have bought some protective gear. Well, I don't earn enough of YouTube to actually buy that protective gear, but in theory, right? I could have bought some protective gear. I could have actually set it up correctly, and I could have actually made the reaction happen. However, I'm not an expert, so how can I be sure that the dangers I took into account are all of them? How can I be sure that there isn't some sort of danger that I'm missing out on, some sort of danger that I didn't consider? And in that case, that danger could be lethal. That's why experts can do a lot of dangerous things, and that's why we, me included, non-experts, we just kind of have to listen to them and take a lot of precautions. And even if something isn't corrosive, even if something shouldn't be dangerous, it's still better to wear the lab coat and the safety gloves, because you don't know. So yeah, when you're doing chemistry or physics or science in general, just remember, you don't know everything. That's kind of the point. That's kind of why you do science. And so you're not going to be aware of every single danger that's out there. And because of that, you should just play it safe, just in case. But that said, sulfuric acid is done. Actually, this is the second time I'm recording it. The reason why is because I've actually waited for days for those pH testing strips to arrive. And here it is. It's even clearer now. Yeah, I know, it's a comical bottle. The point is, it's really clear now. Really, really clear. There's a lot of electrode junk at the bottom. And I think this might genuinely be some relatively clean sulfuric acid. So let's test it out, shall we? Oh, if you want to know why there's some cables on the left and why this is on the right, once again, Patreon. I'm not gonna tell you here. And what a smooth segue it is, because speaking of Patreon, whilst, you know, past MAKiT is setting it up in the background, I might as well tell you about Patreon, or at least thank some patrons for this month. Because see, without Tefta, without Ali, without Kuand, without Useless, without Oregano, and without Ryan, this really wouldn't be possible. This video would be really impossible, and I mean, the chemistry is expensive, okay? And I want to do even more practical videos from now on, which means buying even more chemical stuff. And so, really, without this Patreon support, I'll be doomed. I'll be doomed to fail. I have bought so much sulfur, and I didn't even use it in this video. I'll have to make another video on sulfur. And if you want to know about these videos before they happen, subscribe on Patreon. I'll let you all know there. I would also like to thank Discreet Fallen for donating on the comment on the additional quantum mechanics video. I did not even know you could do that on YouTube, if I'm being completely honest. Anyhow, that's it. Thank you all so much, my dearest beloved interns. And thank you, dear viewer, for watching this video. And I really hope you enjoyed. Anyway, here's the test. There we go. Oh, it's turning red. Oh, that's really red. Wow. Oh, oh yeah. Oh yeah. Well, do we even need to? That's that's just wow. Wowee. Wowza. Wowza, wowza, wowza. Do we even need to, like, wow. You can see the, oh my goodness, that is either a 0 or a 1. It's hard to tell. I feel like it's near 0. That is, wow. I was honestly expecting it to be like a 3 or a 4. I know it's sulfuric acid, but I don't trust myself with making sulfuric acid. I honestly thought it was gonna be a 3 or a 4. I wasn't expecting a 0. That's about as good as you can get. You can't really get better than 0. Wow. Just... wow. Yes! We made sulfuric acid! Oh, hell yeah! And it's so clear, too. Oh, yes, I am... we're awesome. Everyone, we're pretty awesome. Oh yeah, and there was like another take where I just like explained why we wouldn't making a full bucket of sulfuric acid, and you can see me comically pulling out the jar out of the bucket and being like, "Yeah, there's a bucket of sulfuric acid, but not the full one." But like scrapped it a bit for time because it wasn't good enough. The whole conclusion of that chapter was that, like, you know, because my package with 2 kilograms of copper sulfate got delayed, I'm not gonna do it this video. I'll actually have a whole separate video in which will make 4 kilograms of sulfuric acid, which will be coming soon, and also pretty expensive. I would need to buy a platinum electrode for that, but like that's why we didn't make a full bucket of sulfuric acid, because my package got delayed for 2 weeks. That's a cool way to end the episode, isn't it? Yup, it sure is. Anyway, for now, that'll be it. Thank you everyone so much for watching, and have a great day. Bye.